pairings that are going on down there, and also comes from mines where a lot of similar work is going on. Really fun to kind of see some of the academic work that's going and get connected with some of our industry problems. Today, Jesse is giving the first of 2 talks. This one's going to be on aliasing, or alias file petrophysical aliasing. His next talk coming up, which we'll send out shortly after this, is on a support tool for log top picking. Both of those are real exciting tools for thinking about how expert sort of interpreters can pair well with algorithms to change their workflows and do better work or focus on the more important parts of their project. So really excited for both of these talks. And as an aside, we're also working with Amanda Cohn at the Denver Earth Resources Library to build a competition for helping them convert some of the data that they have to a database of some kind. So that's going to involve taking scanned documents that they have and getting people involved with OCR, value of information, database management, georeferencing to better help them work on digitizing the entire library. Those are early days, but we're working on that. So if that's some things that interest you or you'd like to get more involved, let us know. And in the near future, we'll be putting together some sort of competition, hopefully with some prizes to get that kicked off. That's all I have for today. For the moment, I'm real excited for Jesse's talk on log aliasing. Jesse.
Yeah, thanks for the introduction. I'm really excited to be here and kind of share everything that we've been working on. Let me pick a screen here. And all right. If you can't see my screen, yell out and I will see if I can fix it. Perfect. All right, so I'll go ahead and get started. Like Kurt said, today I'm going to be talking about our Python package that we've developed called Alaska. It's the digital well log aliaser. So it works on LAS files, and it's work that we've been doing down here at UT Austin. Primarily, probably 95% of the work has been done by one of my students, Destiny Dong. She is the primary author on pretty much all of this. And then myself and Michael Pyrcz kind of stand in the background and cheer and go, wow, this is really cool, and work on this. All right, so first off, I have to give thanks to those that are giving us funding. So thanks to ConocoPhillips, they sponsor our research group here at UT, so the Freshman Research Initiative. They sponsor, I think it's 25 students coming through my program over the course of 2 semesters. We work on subsurface and digital, kind of the intersection of digital and subsurface. And that's in the College of Natural Sciences. And also give a shout out to the Texas Advanced Computing Center. They provided us resources to, I think we ended up with like 500 hours worth of free compute time to train up a whole bunch of models that we used in this package. So with that out of the way, I'll give you a brief outline of kind of what I'm going to talk about for about the next hour and a half. So we'll start off with background. So this is the kind of high level overview. Why did we build this? You're going to get to maybe throw your hand in at aliasing a couple of well-log mnemonics. We'll talk about the implementation, kind of the theory behind it all. We'll do a quick data breakdown on what this actually looks like kind of in a production sense. Then we'll go through some very cookie cutter, happy, real world examples. I'll show you how to parse a single LAS file. Then we'll parse through 33 what we've decided are kind of our edge case LAS files that are pretty messy. And then we'll parse through about 700 LAS files that are like much more easy, happy, cookie cutter files. I've got a shared document. If you want to take notes, ask questions, I've got it up on another screen here. So if you've got questions, comments, this is a great place to write them up. That way, at the end of this, we also have a copy of kind of all of our notes and thoughts. And it'll come in handy when we're trying to alias things by hand. And I promise this is probably, I think this is the only meme that I've got in this presentation today. All right, so let's go and start with a little bit of the background and start off with why did we build a mnemonics aliaser? So the long story is when you read in data, LAS files, you can have like 3 different shallow resistivities of varying degrees. You can have a medium resistivity, a deep. You might have a gamma ray. You might have a environmentally corrected gamma ray. If you're doing petrophysics, you probably want all these different curves. If you're kind of doing high level, I think Thomas said earlier, 10,000 wells in a data set, trying to parse through different vintages of the gamma ray curves tends to be a pain in the butt. You could spend a lot of time aliasing things by hand, which ends up kind of being this like circular n factorial time complexity where you're aliasing things back around to themselves, and it just kind of gets out of control. So we don't want to have to do this manually by, say calling these our shallow resistivity. We don't want to have to go through and alias these things to shallow resistivity by hand. So, and especially if you're going through a data set and it looks kind of like this, unless you're working with these things on a daily basis and have a good feel for what each one of these are off the top of your head, this isn't really efficient to be able to look at these. And, if you onboarding somebody quickly, you want them just to know kind of what it is. Is that what we're calling shallow resistivity? Is that what we're calling medium resistivity or deep resistivity? So that's kind of one of the reasons why we built this. And actually, Zane brought this up earlier, was this tweet from Zoltan, also here at UT, a couple of years ago, that he went through 300 well logs and kind of tried to parse through looking for gamma ray based on just things that started with GR, and this is what he came up with. So kind of actually not kind of, it's very messy. So this is kind of one of the main reasons we built this thing. So we can have data sets where we can look at these and intuitively have the descriptive depth caliper, density porosity, density correction, neutron porosity, gamma ray, PE effect. So this just really helps readability. And this means that you're not just kind of like, okay, here's a alphabet soup of mnemonics that maybe 5 people in your company understand. When you have your data in this format, a lot more people can easily access. I guess it's a lower barrier of entry when you can label up your data like this by hand. All right, so seems trivial. Seems like a really easy thing to do. So here's where you all get to kind of play along with me here. So here's some mnemonics that I just picked kind of randomly out of a well log file that I've got here. Let's see if I can chat over here. Slightly larger. It's not showing up for some reason. Let's see, there it is. Okay. All right, so let's go ahead and start off with some mnemonics. So this is where you'll get to play along. What is our top mnemonic? What do you think ECGR would maybe alias to if you're trying to get at all your wells across a basin? So environmentally corrected gamma ray. Yeah, most likely. I've seen that one before. I imagine some of you have seen that before. How about RHLA? Anybody know that one off the top of your head?
I don't.
How about any of these other ones on here? Anybody know these off the top of your heads? Some kind of porosity log, CTEM, maybe temperature, BS, yeah, bit size. So you know a couple of them, maybe ones that you interact with on a frequent basis, off the top of your head. What if we said, okay, what about, let's look at units. Does this help at all? Does this help you kind of make your interpretation of what these mnemonics might be a little bit easier? Yeah, so this gets a little bit easier when you've got units in here. Most of the time, people are just typing these into, you know, some kind of web search. Maybe you've got something at your company where you're just typing these in to figure out what these are. Now annotate. Okay. All right. So units make things a lot easier. When we add in, say, a description in here, it gets a lot easier, does it not? So when you've got your mnemonic, your units, and your description, you know, this is the straight up description, just gamma ray. So we've got a parent density, invaded zone resistivity, bit size, cable speed, cartridge temperature, an array induction, resistivity, environmentally compensated log processing. So adding in these kind of different features really helps with your understanding of what these mnemonics actually are. So seems trivial. We did okay. With our kind of group here, we did all right. Seems easy enough when we parse through and look at the mnemonics and we look at the units and we look at the descriptions. So that was 7 mnemonics from one LAS file. That file alone has 56 different mnemonics, and it looks something like this. So this is what that LAS file looks like. So you can see we've got our mnemonics on the left-hand side here. We've got our units and then some kind of a description over here. So a lot of the easier ones, you might know off the top of your head, they're easier to alias. Some of these other ones that maybe you run across it like once in a blue moon. So this is where this tool really kind of starts to come into its own. All right, so the big takeaway that you should, I guess, take away from kind of this section of the presentation is that it takes a lot of time to build these alias tables by hand. Time always equals money, no matter what industry you're in. And generally, this is kind of boring work. I've built alias tables by hand, and it's not a lot of fun. You just kind of parse through, okay, I have 10,000 LAS files. Okay, let's go through and see if we can nail down every single one that has a gamma ray in it and alias them all to gamma ray. It's not a lot of fun work. It's one of those things that you set that timer for 20 minutes and go to town for 20 minutes and then get your 5-minute break and just like stare out the window and contemplate your life choices. So the big question is, how do we automate this? Being that it's, I was going to say that it's 2020, but we started this in 2019, started really thinking about this. We want to use Python. We want to use kind of these digital technologies that we've got. All right, so let's talk about our implementation. How did we build out this Python package? So first off, let's go back and think about how did we do this by hand? So we'll start off with our ECGR mnemonic. That one, seen it before, know it's a gamma ray log. Okay, so that's pretty intuitive. We have somewhere in our memory, we've seen it before, we know how to alias this. Okay, so that seems pretty easy. All right, how about RHLA? So for that one, if we look at our units, we've got grams per cc. So that's got to be a density of some form. So we're talking about density if we look at our units. So that kind of makes sense by looking at units. How about RXOZ? This one, the description said invaded zone resistivity. So what I guess, what word would you take away from this description here that would describe this mnemonic from a human perspective? Yeah, some kind of resistivity here. All right, so the summary for this. So we can look up what we know. So we can look it up. We can look at units, that's really helpful. And then we can pay attention to important words in the description. So in this description, these were kind of what seemed like our most important words. And really, when you look at this, you're just kind of focused on, oh, resistivity, your brain, your neurons are lighting up and going, oh, it's just a resistivity log. So how can we re-implement this and teach a computer how to do this? So this is where our package comes in. Let's talk about kind of the makeup of Alaska. So it's got 3 primary components. So the first component is a dictionary. So if we go back to how we parse through our mnemonics, we're using basically a dictionary search or a lookup table. So we're looking for exact matches of mnemonics to the ones that we have in some dictionary, be our brain, be the Schlumberger online search, Cranes, whatever you want, whatever dictionary you want. In our package, this dictionary literally is just looking for those mnemonics, looking for that string of letters. If it finds it, it says ding, 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 that's a caliper log, and returns caliper. So that is now alias to caliper. If it doesn't find it, it says, well, it's not in the dictionary. Let's pass that on to our keyword extractor. So our keyword extractor, it looks for what we've classified as keywords in the mnemonics descriptions and assigns labels if the keywords are found in the tree. So I've got a slide to kind of to more easily visualize how this is working. And this one's pretty handy. After that, it's if you don't find a mnemonic in the keyword extractor, then it's going to pass whatever it didn't find onto the pointer generator model. So this is where, like, these first couple make sense. This last one is where things get really kind of interesting. So this pointer generator is a sequence-to-sequence recurrent neural network that reads the description, figures out what words are most important, and summarizes it to 2 words. So cuts it down to 2 words and says, here's what I think they're talking about. The cool thing about this is it's also got a probability cutoff. So you could say, I'm only interested in the pointer generator if it's got 90% probability that this is the right answer or above. Or you can say, whatever 10% probability and above is good enough for me, and just let it go. So this is kind of our 3 main components here. So it starts with the dictionary, searches for what it can look up, passes to a keyword extractor, searches for what it can find there, and all else fails, passes it off to the pointer generator. So let's get a little bit more in depth on these. So we start off with our dictionary. This is the most boring slide of this talk. It's really, really easy. So here's our mnemonic, HDRB. In our lookup table, we've got HDRB corresponds to a caliper log. So in our dictionary, we have, let me see if I can grab it here. Here's our comprehensive dictionary. So we've got a little bit of everything. So on the left, we've got our mnemonic. On the right, we've got our label. And we spent some time with a web crawler, basically pulling these off of every single website that we could find to pull mnemonics and figure out what they corresponded to. And so we've got about 1,200, a little over 1,200 entries in our lookup table. This is where in our package, if you have your own lookup table, if you're like, I want to split out environmentally corrected gamma ray from gamma ray, you can open this up, edit it, and save it back onto your local machine. Continues working, no problem. So you can change this thing to however you want. Any of these things that are in here, you can add to it. So this is where you can start to add in kind of customize what you want these labels to be. So if you don't want it to say neutron porosity, you can change it to whatever you want. The sky is the limit on this. So this is kind of the starting point of how we can customize this package. Any questions on the dictionary lookup?
How much did you scrape from Welly? I guess Welly just scraped it from Cranes with some extra pizzazz. So, but now Cranes is behind a password. So,
yeah. So we scraped everything in fall 2019 from pretty much everything that we could find on the web. So if you've got updated versions, I know there's a SPWLA lookup table somewhere.
Tegwin Perkins built it. It used to be public, and I don't think it's available anymore.
Yeah. So if you want to, if anybody wants to add to our dictionary lookup, man, this thing's slick. It's fast. It's really fast. Our dictionary lookup, it takes on average. I timed it out today. It's about for really weird edge cases, it takes about 2 seconds per file to parse out. Let's say 50 to 60 mnemonics takes about 2 seconds in our dictionary.
Does it have any prioritization? So if you had different things that were coming up as deep resistivity, say, do you have any control over which one would get used, or is that something you'll talk about later?
So we haven't set up any like, you know, if you want to use like, yeah, I guess a different version of deep resistivity over another. At this point, we've just lumped them all into one and said, however you want to parse it out, you can access all of the deep resistivity using something like Welly just by calling deep resistivity, and it'll return back all of the ones that are labeled that.
yeah,
But that's, yeah, go for it.
Yeah, because Welly does it via the Cranes gut ranking of that. There's an order that Mr. Crane has.
Yeah, it's. I think that'd be would be a very interesting addition to this, to have some kind of ordered ranking of, you know, what do you want first. Right now, we figured it'd be easiest just to lump it all together and let you kind of sort out which ones you're most interested later on down the road. Any other questions on dictionary lookup? All right, let's go to our keyword extractor. All right, so this is where things start getting a little bit more interesting. So here we have our keyword extractor. So our example description is SLDT, QLDT, high resolution, density, porosity. So what our keyword extractor does is it's a m-ary tree. So just like a parser in pretty much any programming language, it's going to start at the root, kind of up here at the top of our tree, and it's going to come down, and every single word in here, it's going to look for a keyword. So in this case, it's coming through and it's like, I don't care about these. I don't care about these. Oh, density. I know about density. And so in the keyword tree, it comes down, it finds density. It says, okay, we found density. And then it says, what comes after density? So after density, we've got porosity. And so at this node in our tree, at the density node, it can split either to correction or to porosity. So if it goes to the left, it becomes density correction down here at this leaf on the bottom left. Or if it takes this right split here for porosity, it ends up with density porosity. So it's got a bunch of different keywords in here. Density, oh gosh, we've got all kinds of things that we thought that were kind of interesting keywords that were in our description. This m-ary tree was built by hand. So this one was a human level brute force of, okay, let's go through and figure out what our keywords are and what possible permutations we can have of them. So the keyword extractor's saying we don't care about the mnemonic, let's just look at the description and figure out if we can find these important keywords in it. Any questions on how this works?
What happens if you just have typical old, like if the keywords are bad, it doesn't really have keyword, well, just like, could you have a flag or like a bork, like there's not a lot of keywords and this well log file is not great. Please manually look at it.
So what it's going to do, if it goes, so it'll go through your keyword extractor. Okay, actually, I'll come up a level. So it'll go through the dictionary, look for things. If it can't find it in the dictionary, it'll then pass it on to this keyword extractor. The keyword extractor will try all of the well log, all the mnemonics in the LAS file. And if the keyword extractor can't find anything in it, then, and I'll show you a little later, it basically comes back and says, here's the list of things that I have no idea what you want me to do with them. So it'll return back things that it's like, I don't know, you sort it out at this level. So it's pretty, I guess the term is, it's human in the loop friendly. Does that answer your question, Thomas?
Yeah, for sure. Thanks.
Cool. All right, so this is our keyword extractor. So as I alluded to, if it doesn't pick out any keywords, then it either returns back or it can pass on to the pointer generator. So let's get into the pointer generator. This is where things are going to go from wild to slightly more interesting level. So our pointer generator. We'll start off with our example. So our source text down here at the bottom is cubic meter per cubic meter, enhanced thermal neutron porosity, parentheses, matrix sandstone, and then we've got our mnemonic on the end here. So this is an example that I'm going to walk through. I think it's like the next 5 or 6 slides, and we're going to talk about how this works. This example is, we basically at this point said it's going past our keyword extractor. So this neutron porosity, our keyword extractor would have picked it up and spit back neutron porosity. But let's just say, for sake of this presentation, that we pass this on to our pointer generator. All right, so this is the architecture of our pointer generator model. And this is where I am going to read from my script. Make sure I get this 100% correct for you all. Okay, so the pointer generator is a trained sequence-to-sequence recurrent neural network. We train the weights to make predictions of possible labels for the mnemonics. In this example, our source text is a mnemonic description down here at the bottom that starts with cubic meter per cubic meter, enhanced thermal neutron porosity, matrix sandstone, and then we kind of cut it off because it doesn't really fit on here. And we're in the process of producing our abstracted label down here on the bottom right. So the first step, we have a encoder. So this encoder that's highlighted in yellow, it basically goes through and reads the source text word for word. So it starts off and says, okay, cubic per cubic, and it basically reads through the entire description from beginning to end. This is a bidirectional encoder, so everything kind of knows where it's at in the sentence. And these little arrows in here represent that the encoder kind of knows what comes before and what comes after each of the words in the sentence. So this is our encoder. So it reads in our sentence. Once our encoder has read the entire source text, our decoder, which is on the bottom right-hand side, begins to output a sequence of words that should form our summary. So at each step, the decoder on the right-hand side here receives from kind of our encoder over here and our context vector up here. It receives the input of the previous word in the summary. So to begin with, it's got this kind of start token here. So it just says, here's a blank entry. Now let's look and see what word seems to be most important. So the first thing it does is basically looks through and calculates an intention distribution. So here it goes through and looks through and says, okay, first thing, neutron would be our most important word to begin with. And so it picks out our neutron and goes through our context vector and summarizes our description as neutron. Then the next word pops up and says, okay, what is next important after neutron? So it looks at our attention distribution and it says, okay, after neutron, porosity is the most important. So let's see, I've kind of derailed myself. So in the diagram above, the decoder has produced the first word neutron and is concentrating on our source word porosity to generate that word. So to get to porosity, so we've got our start token, we've got our word neutron that it summarized, and now to get to our word porosity in here, the attention distribution is used to produce kind of a weighted sum of the encoder hidden states. So this encoder down here has a whole slew of hidden states that put these words in context. You can think of the context vector as kind of what's been read before and what should come next is represented by our vocabulary distribution and this kind of final distribution. So your context is what has it seen or what has it summarized so far? And our vocabulary and final distribution is what should come next. So the context vector and the decoder hidden states are used to calculate the vocabulary distribution, which is this guy over here, which is a probability distribution over all the words in a large fixed vocabulary. So in our case, we're looking about 10,000 words in our vocabulary. The word with the largest probability is then chosen as our next summary. So the main thing to take away from this is that it's looking through this encoder, saying what are the most important words, picks out the first most important word, say neutron, then it looks at neutron and says, okay, what's typically follows neutron in the 10,000 words and cases that I know? Well, it's most commonly porosity. And that's our summary, just these two words here. So we're basically, if you've ever used those, I want to call it services on the internet that take a news article and summarize it down to like 1 or 2 points. This is doing that, but we're taking a sentence and shortening it down to literally 2 words. So this is where things kind of get fun. Any questions on the pointer generator? It's a fancy, fancy way to say we're taking a sentence and shortening it down to our 2 most important words.
Is there anything that relates to sort of the uniqueness or how distinct either of the terms are compared, as in how much they distinguish between various words as opposed to just being super common?
So we trained on, we basically scraped a whole bunch of data and said, okay, here's what we know so far. How common in well-log descriptions are these sequences of words? And then we also added in the units as well as the mnemonics, just to kind of bump up our, basically bump up the word count in the description. And so it's looking for oil and gas well logging specific terms. Does that answer your question? Kind of. And we'll get a little bit, okay, so the pointer generator is really cool, but it can throw out some really weird stuff. When you let it run kind of wild, it comes up with really, like, some make sense, like, yeah, that's cool, and other stuff, not so much. But I'll show you on this next slide here. So those are our three components, and we're going to get a little bit further into that. Let's go through a quick breakdown of our data that we kind of tested this thing on. So the data that we used is gathered from about 2,000 well logs. There's 1,500 or let's see, I think there's like 15 or 1,600 mnemonics in these 2,000 well logs. So our dictionary took care of about 60%. Cool. That's stuff that we're really confident in. Our dictionary is just our one-to-one lookup. This is something that we feel good about. Our keyword extractor takes care of about 20%, which that's a pretty good chunk. So now we're 80% of our well logs have been automatically aliased with somebody just kind of hanging out, watching this thing do its thing. All right, so now we've got our last 20%. So 15% of that we can wrap up with our pointer generator with a confidence greater than 50%. So this is saying, give me everything that's got a probability greater than 50% of this actually being a correct summary. And then this last 5% is things that are very, very edge case. So these are our weird mnemonics, our weird descriptions that you don't really run across very often. And these are, we're down at our 5%. This is the realm of, like, the computer does okay, but these are the things that you should probably look at as a human and say, well, do we really think that water porosity is an actual thing? All right, how's everybody doing? Is everybody still awake? Everybody still with me?
Yes.
Oh yeah.
Excellent. Okay, this actually is perfect. This is the time I normally teach my classes, and it's like this time of day, we lose about half the people online. All right, so now that's the theory part. Let's go through some really fun cookie cutter examples. Let's learn how to use it and parse through kind of a variety of different stuff. And I think somebody I saw in the chat, this is our GitHub page, and this is where I'm going to next to show you kind of the basics of how to use it. All right. So let me start off here. All right, so this is our GitHub page. I mentioned this is all open source. You can download it, change it, do whatever you want. If you've got ideas, want to contribute, we are 100% open to changes and updating things as we go. So we have a getting started guide down here. I'm not going to go through the installation with you because that could take a while, but the biggest thing is if you clone a copy of our repository here, we have everything to get you started. I feel like a salesman right now. We've got everything to get you started. So we've got an environment that will set up a virtual environment for you. It's got almost everything you need to get started. In that environment, the only thing you have to install by hand is PyTorch. And that's because if you're on a NVIDIA GPU, you need to pick the correct version of PyTorch that jives with your system. Other than that, everything else comes in our virtual environment. So basically create a virtual environment, activate your virtual environment. Once you're inside your virtual environment, the easiest way to do it for now, we're still in beta release. We've still got some things to kind of iron out. The easiest way to do it is just run the Python setup from kind of from the clone directory, and this will install it on your machine. So that's the, and I know it's the like quick and like super easy way to get up and started. If you have questions, please open up issues on GitHub, send me messages. I accept messages by carrier pigeons, dog sleds, Morse code. If you can get a message to me, I can help you out with it. So that's kind of the high level overview of how to install it. We've got some quick sample usage down here, and this is enough to like kind of get you started, to get your feet wet. So what I'm going to do is I'm going to open up, and we're going to start off with parsing a single LAS file. All right, so we've got it installed. I'm in a virtual environment. Right now I'm in Jupyter Lab, so I've got a Jupyter notebook open. And we're going to play with Welly and Alaska. So this Welly import, we'll use this later on. Our most interesting thing that we care about here is we want to import our alias class. So this is our class that does all the hard work. This is what we just talked about for 30 minutes, is this class right here. So we can go ahead and run those imports. So Welly for kind of messing around with stuff, or organizing our logs. Our aliaser from Alaska, and then some plotting functions. All right, so I've got this LAS file. So this is the one that we went through, oh gosh, and did 7 logs out of by hand. So this is the path to that well log. So I'm just going to set this path as a string so that we can read it in. All right, so the next thing we need to do is create an instance of our aliaser class. So this is the quick and easy way to do it. This is just saying, we don't care, give us all the defaults, and just create an instance of our class here. So we've got that assigned to this variable A now. All right, so now let's parse and see how it did. So what this is going to return, so we've got our aliaser class, and if you've ever used like scikit-learn, we tried to somewhat emulate and make it easy for you to call the methods. So we've just got our instance, and we're just going to parse. So this is going to parse our log file path up here. So this is our LAS file, and we're going to parse it. And what it returns is a dictionary of what it parsed, so what it found, and then it's also going to return a list of what it didn't find. So if we run this, it'll give you a little kind of readout. So reading 57 mnemonics, and it's going to tell you what it's doing with the dictionary. So alias 39 of those 57 with the dictionary, ran through the keyword extractor, and alias 8 mnemonics with the keyword extractor. So then we've got this cell here, and this is just going to print out what we've got, basically what we found so far. So here's our alias dictionary up top. So we've got depth, shallow resistivity, medium, deep, caliper, density, porosity, gamma ray, density correction, neutron porosity, and so on and so on and so on. And then down here at the bottom, we have our not found. So here's the things that it didn't parse. So here's the mnemonics that it basically said, I went through the dictionary, couldn't find them. I went through the keyword extractor, couldn't find them. And these are things that you should probably look at. So these are our not found. And note, and we can kind of dive a little bit further into this, the default is it's only going to start with the dictionary and the keyword extractor. The pointer generator by default is turned off. Because it's more of a human in the loop type situation with the pointer generator. So these are things that are not in our dictionary, and we were not able to parse out with our keyword extractor. Okay, so we've got these kind of built up. We can create a list of our keys from our dictionary. So these are basically what we've aliased everything to. So instead of saying, BS, we've got bit size down here. So this is our human readable set of keys here. And now this is using Welly. So we imported this project class from Welly, and we're just going to read in our LAS file into Welly. And then we can turn that into a data frame that's aliased with our dictionary. So we've got all of our different curves up here and depth, and you're off to the races. You can do whatever you want from here. So let's say you've gotten that far and you're like, I'm kind of curious to see, how the alias dictionary, how confident we are in things. So what we can do is we can take our alias class that we created an instance of up above, and we have a heat map function. And so what this does is it plots out our confidence in our aliases, and it'll tell you what did what. If that's not vague enough, so it'll tell you, like our dictionary aliased these three. Our keyword extractor alias that one, basically these ones down here. And it's giving you a probability of 1 for every single one of these things. Basically saying we found it in our dictionary, we found it in our keyword extractor, so we're pretty confident that we know what this actually is. And I think I added these on here. So you can basically grab from data frames from the Welly data frame using your human readable aliases here. But you can also get at it using the original mnemonics if you wanted to as well in Welly. So it's kind of cool. This is where we kind of like say, okay, we did our job. Now you get to do whatever you want to do. We've provided the tools for you to alias these things and make a decision on if you like the alias or not. And then the last thing down here that I've got is because it is a dictionary, let's say you're working in Petra or Petrel or whatever, you can take that dictionary and just save it out as a CSV. So you've got your dictionary, you can just push it out to ASCII format for reading into whatever you want to use. So that's an option as well. So this plays nicely for, you can alias open source and then go back to Petra, whatever you want to do is fair game. Any questions on this so far? While you're thinking about that, let's come up here and let's look at our this parse method up here. And sorry, let's look at our alias class here and see what all our options are. So in our alias class, your default options, you're going to parse with a dictionary, you're going to parse with a keyword extractor, and then this is where you can change. If you want to use a pointer generator, you just change model to true, and then you set your probability cutoff here. And let's see, a question in the chat: for a mnemonic that is not in the dictionary and doesn't have a description, would it appear in that list not parsed with the aliaser? Yeah, so if it didn't, let me come down here. So these are mnemonics that it did not find, that it did not parse, and these are things that it wants you to look at and make a human decision on. And so let's come back up here, and I'm going to change our alias instance. I'm going to say, I'm going to set everything to true. And we'll use our probability cutoff, our standard probability cutoff is basically 50% probability. So this is going to use our pointer generator model. So we'll run this, and this is going to create our instance A. and come down here. And if I run this again, it's going to think, and my poor little laptop's going to scream while all the fans are running. And so it's telling us kind of what we saw. We've got 57 mnemonics, 39 are parsed with our dictionary, 8 are parsed with our keyword extractor, and then it loads up our pointer generator and tells us that it aliased 10 mnemonics with the pointer generator. So now we can come down and see, what do we have here? So this is telling us what our alias dictionary, so these are what we were able to alias. And here's the last, here's 4 that it said, even with a pointer generator, we don't know, good luck. You should probably look at these mnemonics. And so here's one that you can see that the pointer generator aliased, called it apparent resistivity. Pretty handy. Any questions on parsing a single? Oh, actually, let's go back down. Okay. All right, I've gotten distracted. Okay, so we've now run our pointer generator. Now we can actually come down here and say, all right, let's come down and look at our heat map again. So if we run our heat map, we should see something a little bit different. So here, it's rescaled itself and said, okay, we've got a probability of 1 for all these things we parsed with our dictionary and with our keyword. And we can actually look at what the pointer generator aliased and kind of make a decision about how we feel about, is that RHLA gave it about 60% probability that that's correct. So you can actually make decisions on how confident the pointer generator was in making these aliases. Any questions on this so far? Largest batches of wells I've run. So this afternoon, and we can run through it. I ran through 700 wells this afternoon in a couple minutes. But it really depends on the quality of the LAS files you're putting into them. So a lot of these, this one in particular is pretty messy in that it's got a lot of weird stuff in it. And we'll go through and we'll run through those 700 wells here. That's kind of my next on my list. But this is like, if you just want to alias one well log and go on with your life, this is the easiest way to do it. Note that because of these parameters up here, you've got 7 different options. So let's say you're like, you know what? I don't like your dictionary. You can get rid of it. If you're like, you know what? I like to live wildly. You can get rid of the keyword extractor and just let the pointer generator run wild. So you can do that. You can do just your dictionary and pointer generator and say, nah, I'm not interested in the keyword extractor. So you can kind of build these to how dangerously you like to live your life. Is the dictionary case sensitive? No, so it basically converts everything to lowercase. So it doesn't care about cases.
Can you talk about those confidence values and how that's built? Seems like it's based on the relationships of the training set.
Yeah, so the probability cutoff is, oh gosh, it's think of it as the confidence the model has that the summary is accurate based on what we trained off of. So it looked at our 10,000 word vocabulary that we gave it and our 2,000 examples and said, okay, how often do you see these two words come or together? So a probability of 10% is like, I'd say 50% is like, what's a good interpretation of a 50% probability of I can't think of it off the top.
Does 50% probability mean that for the two words that are linked together, half of the logs that it's connecting to in the data set had those words connected to that mnemonic?
So imagine we did it for just one mnemonic. So a 50% probability would say that half of those two word summary is correct.
Okay.
So
yeah, so half are not correct.
Yeah. So
yeah,
a good example is when I said water porosity earlier on, that was actually something that the pointer generator returned back when I had it set at like 0.05% probability or confidence almost, basically saying, I think one of these is right with very low confidence. So think of it as like a summed confidence across the two words.
Okay.
Okay, so this is single log, pretty easy, fun to deal with. Let's get into parsing a directory. So it's very similar to parsing a single LAS file, but we took the heavy lifting out of it. So I'm not going to run these because my poor computer is like struggling here. Similar imports. We're still using that alias class. This alias class does everything for us. Here I've got, I've set a path here. So I've got a path of examples. This has got, 33 different LAS files. And these are all really weird edge cases. So these are very, very strange LAS files that have a lot of mnemonics in them. So here we just have to set our path. And then down here, I've said, okay, all we care about right now is just our dictionary. Just parse it with our dictionary. So we come down here and it tells you, okay, I'm reading 70 mnemonics from the first LAS file, 42 mnemonics from, or aliased 42 of those 69 with the dictionary. And then it's just going to move on because we said not to use the keyword extractor and not to use the model. So it's just going to use the dictionary for all these. So it's going to walk through all these. And here in this cell, I said, okay, let's time this thing. So we've got a start time and an end time. And it basically walks through aliases, all these things. And it took about a minute to alias 31 pretty weird LAS files. I timed it out earlier today and wrote down, just because I was kind of curious, I'd never done any benchmarking with it. So it's about 1 minute for these with just the dictionary. It's actually a little bit faster with the, for some reason, with our keyword extractor. So if you run the dictionary and the keyword extractor, it's going to take the same amount of time as it would to run just the dictionary search. And then on this data set, for the dictionary, the keyword, and the pointer generator took about 3 minutes with low probability. So significant overhead on doing inference with the pointer generator. This is our alias mnemonics just from our dictionary. So this is what basically our aliases look like using just our dictionary on this directory. So this is our alias for 31 different wells. So we can see that it's kind of started lumping things so that you can have one alias pointing to many different mnemonics in there. Let's see. Kurt says, does this use close matches or must strings be exact in the keyword and seek-to-seek steps? So are you talking like spelling errors? I think they have to be exact matches if I recall correctly. And because for a while we had looked at, can we use something like a Hamming distance to figure out how close strings are to one another? And went down that road for about a week and then said, let's just build a dictionary for now. But yeah, dealing with spelling errors, in so much geologic data, that's a huge issue, is like somebody typed it in slightly wrong. So yeah, that would definitely be that'd be a cool function to add in there. So this is what our parse directory looks like, or our parsed, our parsed directory for all of our aliases. Took a minute to build for 30 different wells. Here's kind of what our keys look like. And then again, it's going to turn back our set of things that it didn't alias. So here's our whole list of things that it's like, you know what, I didn't find these in my dictionary. Either run it through the keyword extractor or do it by hand or whatever you want to do. So these are things that it kind of spat back at us.
Have you messed around at all with trying to use like distributions of the actual data? It's like certain types of data, might make sense. Like a resistivity would have a different distribution than a porosity or something like that. It might be another piece of information that could help. That
would actually be really interesting to see, if something spans like 4 orders of magnitude versus like, I'm thinking like a gamma ray log. It's like, units. That could actually be really interesting. That could be cool.
Just a thought.
Yeah, definitely. I like that. Let's see. What else did I want to show you all? Oh, so this is what it looks like when it plays nice with Welly. So here I've just grabbed all the aliased gamma rays, plotted them up. Typically goes fairly fast. And then you can, with Welly, shove them all out to tabular format and do what you want with it. And then down here, I ran kind of a couple of different versions. So here we've got, we're just using the dictionary. Here we're using dictionary and keyword extractor. Here we're using all of them with the model and a probability cutoff of 50%, and then a probability cutoff of 1 or 10% down here. And let's see if I can zoom out a little bit here. Get less oppressive. And so what this is so on the y-axis here, we have our unparsed mnemonics, and on the x-axis, we have our number of parsed mnemonics. So here's our dictionary. We parse less than 100. We have 140 that it didn't even recognize. With our keyword extractor, we're just under 100 that we didn't parse. With our 50% pointer generator probability, we're down to less than 20 that it's not really feeling too good about. And then at 10%, there's only one mnemonic that it had no idea about. So you can see we get a pretty nice little, it's a nice linear relationship. And then down here at this end, it definitely gets asymptotic down here when you start using the pointer generator. Oh, my CPU usage is high. Let's turn off the virtual background. All right, so let's see if we can hurt my machine. All right, so let's go ahead and run this for, I've got a larger data set that's a lot friendlier. So that previous data set, it was 31 logs that are all really large, got a bunch of weird mnemonics in them. Here I've got a different data set that's much more friendly. Each log's got like 2 or 3 mnemonics, so they're a lot easier to deal with. If I run this, it's got like 700 different LAS files in this directory. And I think these ones are from Kansas, I believe. So they're a lot easier to deal with. So you've got like 2 mnemonics, 3 mnemonics. So they go a lot faster when you run the aliaser on it. So that's 700 and some odd. And that'll probably take a minute. So the biggest thing to keep in mind is when you're using it, be cognizant of what kind of data you're putting into it. If you've got weird edge cases, the pointer generator's probably going to give you some interesting summaries. If you've got these more like gamma ray and a resistivity, it's going to be a lot faster and a lot happier to deal with. So just kind of be cognizant of that. While this runs, I will take any additional questions, any thoughts, comments.
Have you thought about using the new and improved aliases from the pointer generator and put those back in your dictionary?
I was actually thinking about that this afternoon. Like, how much faster would it be if I got those summaries and put them into the dictionary and started using that as the dictionary search?
Yeah, it kind of would cut down on the neat bar trick you've coded up with your fleet of freshmen, but I could just imagine it might cut down on edge cases, or if you wanted to put this in production or something.
Yeah. And I think the biggest thing with the pointer generator is it's useful, but like all machine learning, you have to be cognizant of, you have to have a human in the loop somewhere, because it's going to spit out weird, every so often it runs across that mnemonic and it just like, it's happy with it. You look at it and you're like, what do you even mean by that? So definitely the pointer generator is where we're getting back to the human in the loop. But yeah, I was thinking about building out a dictionary based on the pointer generator. Could be interesting to see. Other questions? Yeah, go for it.
Even like a regional one, like the offshore UK will have a lot different aliases than like Kansas, than like Permian Basin. Like there's a lot of overlap, but it's still different contractors and stuff. So
yeah, and like so this one that it's running now, I think, is Kansas. The weird edge cases were, I think, the majority were out of Wyoming. And then one key thing to think about is this was a very United States centric training data set we used. So all the units are actually, I think they're a mix now, but they're originally imperial units, so inches, feet, and then we added in some data out of Canada to help us with our metric units for this. We're still running.
For other applications where you're using text and training relationships, do you have any things that you've learned from as you've built this specific implementation that would be useful for keeping in mind for future projects? We try and figure out text relationships.
Yeah, I think the biggest thing for this was figuring out what our edge cases are. Figuring out figuring out edge cases and dealing with unbalanced data classes. So it seems like every log for a while that we went through, every single one had a caliper. So our training data was like 50% calipers. And we're just like, where are all these caliper logs coming from? So making sure our data set was balanced and finding the weird stuff, finding the weird stuff, training on the weird stuff, trying to cover as much of the feature space as possible, so that it can do better when it runs into kind of those weird edge cases. So here's those 700 logs finished running. So couple of minutes to run through 722 LAS files. And because they're not super exciting, here's all of our alias mnemonics, and we can print out our keys, and then we can look and see what it did in alias with just the dictionary. So not too bad. And if we added our keyword extractor in there, it would take the same amount of time, but we'd probably be able to get a lot more of these parsed through just the description. I think, kind of going back to what you were talking about, Kurt, I think one of the big things that we learned is that when you're trying to tokenize text to build up training data sets, finding some kind of way to tokenize that is okay with different lengths. So you might have a description where your description is literally gamma ray. That's the description. And then you have other ones that are like, the very weird mnemonics that are like 20, 30 words. Being able to tokenize those two and be able to train your model with very unequal token lengths for your training data set was kind of a challenge. And that's why we ended up going towards this pointer generators. It deals with varying lengths in the training and in making predictions. Anybody else got any other questions?
Hey Jesse, it's Zane here. Hey man, it's really nice package. I like it a lot. It feels like this could be a perfect, like you could extend this in a hackathon style, or like the hive brain, during some of these conferences and things like that, right? Like a Spanish language dictionary would be pretty sweet, and like I can think of a whole bunch of ways to extend this. So it's a really, kind of inspiring package that y'all built. So it's really cool. Thanks.
Yeah. And it's to add on that, we are 100% open source. If any of you want to contribute, we are happy to work with you. We've been going through building out our tests. We'd love to have more training data. We scraped a bunch from the web and spent a lot of time training. We are always open to suggestions, changes. You want a different feature? We're definitely amped about that.
I have a question, Jesse.
Yeah.
So I was looking at dictionaries, and there are already some mnemonics that I have, but they are not there. So as a user, I will add them to my own dictionary, or that is awarded a pull request for the GitHub?
Kind of depends on, I guess, what you want to do. If you want to, so the easiest way I would say to do it is add them to your local copy, and then open up a pull request if you want to add it into the package, and then we'll just roll it into our dictionary and it'll go out with the next distribution. But if you want to use it locally, you can just update that basic, I don't know if I've still got it open, the comprehensive dictionary. Stop sharing my screen. Yeah, the comprehensive dictionary that we've got, you just add a row in there with whatever aliases you want, and then that automatically updates anytime you'll run through and use the software.
Yeah. So in my case, I have some drilling logs, and I don't see, I haven't seen the full dictionary, so I don't know if they are there, but those are more like wildlife logs. Wildlife logs. Okay.
Yeah, and we tried to throw in some mud logs here and there, and it didn't do so well with those. It'd be cool. It'd be kind of cool to have those in there, you know, like to actually have mud logs in our dictionary so that you could just look up mud logs via a known mnemonic or whatever you want to alias it to.
Yeah. Yeah, for the examples that I have, they have the name, but not the description. So just for that, I was thinking like, yeah, I don't know if it could work, but I will try.
Yeah, give it a shot. And if you want to open up a pull request, we're always happy to look through, and we'll run it through the tests and make sure everything's cool and then merge it in.
Perfect. Thank you.
Yeah, thank you. Any other questions?
The mud logs sound like it would be a good place for Donnie's suggestion for because you get like C1, C2 and starts behaving poorly for alias type approaches. You might want to incorporate numerical information to figure out what you're actually looking at.
Yeah.
This has been really good. I want to remind everybody that Jesse's going to be talking with us again in, I think, a week's time on the correlation support tool they've built to help pair a algorithm along with a log picker, top picker, to kind of get suggestions of where tops should be going, which is another really cool implementation of sort of the expert plus the computer. Does anybody else have more questions they want to ask?
There is plan for an interface for a visualization of, you know, like a easy way to put the log and for this part. How I say that? Yes, it's a visualization tool, you know, like it seems very easy to put in a interface that it will be easier to get the alias files or.
Yeah, so I think the easiest way to visualize that I've found so far is with the Welly package and plotting up wells after their alias, like with our package. I think if you ran through and alias everything and then like exported it out, then being able to import it into something like Petra would really be, I kind of look at that as like, that would be a really easy way to kind of come full circle back to interpretation, be able to not have to worry about aliasing, but be able to go back and pick tops and do correlations and stuff.
Yeah, there's a lot of different ways you could approach visualizations. I think Thomas was showed off one when he did his collab session as well. There's a lot of cool options for that. Well, Jesse, thank you so much for talking with us today and putting the time together to put this together for us. This is really good work. Thanks for building the package and putting it out for everybody. And hopefully we can all get some interactions with you from some of the people on the team on the call to add some features and incorporate some of our all of our alias tools together and make this even more useful. The language conversation is a really good one. It'd be fun to make this an international tool. Thanks everyone for joining. Remember to look up and down the list. There's a really good group of people on the each of these calls, and everybody's kind of got different areas of expertise, and so it's fun to get together and find out how different people are using different languages and different algorithms to support their work. We're all going to be the ones making this industry digital in the future, so it's fun to see what different people are doing. So with that, we'll have an email go out shortly with a reminder for Jesse's next talk. Thanks, everyone.
Thanks for coming, everybody.
Stay healthy.
Hi, thanks, Jesse.
Thanks, Jesse.